Good morning, students. Welcome to the Science 1 class. In this lesson, we shall learn about electromagnetic induction. In 1831, Michael Faraday explained the possibility of producing an EMF across the conductor when the magnetic flux linked with the conductor is changed. In order to demonstrate this, Faraday conducted few experiments. Wind an insulated copper wire on a paper or wooden cylinder so as to form a coil in the form of solenoid. Connect the two ends of the coil to a galvanometer and place a magnet close to it. The reading of the galvanometer is 0. When the magnet is stationary, the pointer of the galvanometer deflects towards the right when the north pole of the magnet is moved toward the solenoid. The galvanometer shows 0 reading when the motion of the magnet stops. This proves that as long as the magnet keeps moving, current flows in the solenoid. If the magnet is moved away from the solenoid, current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the left. The deflection increases if the magnet is moved away with a greater velocity. If the polarity of the magnet is reversed and the magnet is brought close to the solenoid, then current flows in an opposite direction. The galvanometer accordingly turns towards the left. Faraday observed that current flows in the coil only when there is a relative motion between the coil and the magnet. The direction of deflection in the galvanometer is reversed. If the direction of motion is reversed, the current in the coil and the corresponding deflection of the galvanometer can be increased by using a strong magnet or by increasing the motion of the magnet. Increasing the area or the number of turns also creates a strong current in the coil. According to Faraday, when there is a no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant. So the galvanometer shows no deflection. But when the magnet is moved towards the coil or vice versa, the magnetic flux changes and an EMF is induced in the coil. If the circuit is complete, the EMF causes the current to flow through it. Based on this experiment, Faraday formulated two laws of electromagnetic induction. Whenever there is a change in the magnetic flux linked with the coil or electromotive force is induced, the magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linked with the coil. The direction of the induced EMF depends on whether there is an increase or decrease in the magnetic flux. Fleming's right hand rule. Stretch the thumb, forefinger, and middle finger of your right hand mutually perpendicular to each other. If the forefinger indicates the direction of magnetic field and the thumb indicates the direction of motion of the conductor, then the middle finger will indicate the direction of induced current. Fleming's right hand rule is also called generated rule. Next, we move on to electric generator. In this module, you will learn about an AC generator. An AC generator is an electric generator that converts mechanical energy to electrical energy in the form of an alternating EMF or alternating current. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft is it can't be rotated rapidly. A field magnet, it may be a strong permanent magnet with concave poles. Two slip rings S1 and S2 and they are connected to the armature and thus rotate with it. Two brushes V1 and V2 they provide electrical contact with the slip rings and a load which may be a galvanometer. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the slip rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means that an alternating current is flowing through the galvanometer. Initially, the armature ABCD is vertical with its arms AB up and CD down. The direction of magnetic field is from left to right as the armature undergoes half rotation clockwise. Arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA. So the current will flow from B1 to B2 through the galvanometer. Now during the next half rotation, arm AB moves up while arm CD moves down. Again by Fleming's right-hand rule, current will flow in the direction ABCD, that is from B to be borne through the galvanometer. Thus, that induced current changes its direction every half rotation. To get a direct current DC, a split ring type commutator must be used. With this arrangement, one brush is at all times in contact with the arm moving up in the field, while the other is in contact with the arm moving down. Thus, a unidirectional current is produced. The generator is thus called a DC generator. Next, we move on to transformer. Transformer is a static electrical machine which transfers AC electrical power from one circuit to the other circuit at the constant frequency. But the voltage level can be altered. That means voltage can be increased or decreased according to the requirement. It works on the principle of Faraday's law of electromagnetic induction, which states that the magnitude of voltage is directly proportional to the rate of change of flux. Two types of transformer is there. A transformer that increases voltage between the primary to secondary winding is defined as step-up transformer. Conversely, a transformer that decreases voltage between the primary to secondary windings is defined as a step-down transformer. Step-down transformer is a device which converts high primary voltage to a low secondary voltage. In a step-down transformer, the primary winding of a coil has more turns than the secondary winding. The formula used to design a step-down transformer is Ns divided by Np is equal to Vs divided by Vp. Ns is equal to number of turns in secondary. Np number of turns in primary. V is voltage in secondary. Vp voltage in primary. The number of turns in secondary winding should always be less than the number of turns in the primary winding transformer. A step-up transformer is a device which converts low primary voltage to a high secondary voltage. In a step-up transformer, the primary winding of a coil has less turns than the secondary winding. Transformers step up or step down voltage according to the ratio of primary of secondary wire turns. Voltage transformation ratio N secondary divided by N primary. Current transformation ratio N primary divided by N secondary. N number of turns in winding. Next, we move on to applications of electromagnets. Let us see the three applications of electromagnets. Speaker. Inside the speaker, an electromagnet is placed in front of a permanent magnet. The permanent magnet is fixed firmly in position, whereas the electromagnet is mobile. As pulses of electricity pass through the coil of the electromagnet, the direction of its magnetic field is rapidly changed. This means that it is in turn attracted to and repelled from the permanent magnet, vibrating back and forth. The electromagnet is attached to a cone made of flexible material such as a paper or plastic, which amplifies these vibrations, pumping sound waves into the surrounding air towards our ears. Magnetic levitation trains. Magnetic levitation, that is maglev, is a method by which an object is suspended with no support other than magnetic fields. In maglev trains, two sets of magnets are used, one set to repel and push the train up off the track, then another set to move the floating train ahead at a great speed without friction. In this technology, there is no moving part. The train travels along a guideway of magnets which controls the train's stability and speed using the basic principles of magnets. Medical system. Nowadays, electromagnetic fields play a key role in advanced medical equipments such as hypothermia, treatments for cancer, implants, and magnetic resonance imaging (MRI). A scan can even minute details of the human body. Many of the medical equipments such as scanners, X-ray equipments, that other equipments also use the principle of electromagnetism for their functioning. That's all for today's class. Thank you, students. Have a good day.